So today we're going to talk about what is distance to fault. We'll go over a little bit of setups required for distance to fault. And we'll talk about the different things that I need to know. And then we're also going to learn how to interpret a sweep. And we'll talk about some of the tips and best practices. I first wanted to discuss a couple of the questions that we had from last week's discussion. And one of the poll questions from last week asked, can anyone add to the list of what causes an impedance mismatch? We had several responses: recessed center pins on connectors due to non-captivated center pins, cattle or rats chewing the feeders, ice damage, ice buildup, nail in the line, water in the line, a forest fire, and an antenna that is not resonant. We got a lot of responses from everybody out in the audience, and we really want to thank you for all these great responses. Another question that came in was, if you set a sweep frequency range and then calibrate, when you recall the sweep, does it retain the calibration? This one is a little tricky, so I'm just going to say yes and no. When you saved your sweep as a CST file, meaning you had it set for the cal plus status, the saved sweep will save all the settings and the calibration. When you recall that saved sweep, it will restore all the settings, including the calibration, from when you saved it. But if you are currently on a new sweep with new settings, it will be overwritten. And that's why I say yes and no. Another question is, what is the difference between return loss and insertion loss? Some people get confused with this. So I'm putting up, by definition, return loss is the ratio of the maximum forward power in a transmission line to the power reflected back to the source. It's expressed in decibels. It is a measurement of how well system components match. And that was another poll question last week. What do we want to match to? Well, the answer is 50 ohms. So all the components, we are checking to see how well they're matched to 50 ohms. Insertion loss, on the other hand, is also known as cable loss, and it is the signal power lost within the feed line itself, including signal loss at joints, connectors, transitions, adapters, etc. Insertion loss takes place in one direction in a feed line, and is the amount lost between the input end of a cable and the output connector of the same cable or system. Insertion loss is measured in dB. And now I have a question for the viewers for this week. When Bird first introduced the site analyzer many years ago, it was geared for the new cellular industry that was beginning to explode. But over the years, other industries have been using it as well, such as aviation, railroads, and public transportation, just to name a few. RF is RF, no matter what the industry is. Basically, a system has a radio, coaxial cable, and an antenna. What industry are you in? And I encourage you to send in your questions and just tell us what your industry is in so we can have a better understanding of what you do. And you can enter in your question or the answers to this question throughout today's presentation. So distance to fault, or DTF, what is it? It is a measurement of how far from the test point of the SiteHawk a fault occurs. Instead of hand over hand checking of the feed line up a tower, the analyzer will give a distance to the problem or fault. The field technician might still have to climb the tower remove ceiling panels in a building, and crawl through tight spaces. But he or she will have a much smaller area to check to find the fault. What information do I need to know? If you remember from last week when we did a measure match sweep, or maybe sweeping an antenna, all you needed to know was the frequency range. Well, for distance to fault, we also need to know the frequency range of the system. We also need to know the cable type. We need to know the total length of your system. And if you have a diagram of your system, that is also helpful, but it's not mandatory. So let's talk about the frequency range of the system for a little bit. When you perform distance to fault or DTF sweeps, widening the frequency range results in a display with more detail visible. When measuring a transmission line with no frequency sensitive components attached, such as an antenna, a large frequency span of measurement, the more detail will be seen in the display. The greater the frequency span of measurement, the smaller the maximum distance that can be measured. The maximum distance is inversely related to the frequency span of the measurement. In general, select your frequency range for optimum resolution without exceeding the frequency range of the attached components, and while maintaining a distance large enough to see all the antenna system components. And add approximately 10 to 20% to the known cable length. The cable information we need to know, there are two parameters for every cable: velocity of propagation, or velocity factor, and cable loss. The velocity of propagation is the reduction in signal speed as radio waves travel through a medium other than free space. This is also known as velocity factor. Entered incorrectly, it affects the distance of a DTF sweep. Cable loss. This is how much power is being lost within the line or in individual components. It may also be called insertion loss, cable loss, or attenuation. It is a manufacturer's specification. Entered incorrectly, it will affect the amplitude of a DTF sweep. These are two very important factors to remember. Entering the wrong velocity of propagation or cable loss is cumulative with cable length and becomes more pronounced with distance, meaning the further away from the test port, the more error that is introduced. And we will see further on, I do have a couple of examples, what happens if you enter the wrong velocity propagation or the wrong cable loss value. I mentioned it's very helpful to have a system diagram available. I know it's not always possible, but it is helpful. This will help you pick out when you are examining your sweep results. You can see the antenna, you can see the different connectors. And without a diagram, it is difficult to tell what you are looking at, and anything you see would be a guess. Regarding the total length of your system, add it all up and then add 10 to 20% to the stop distance. This will ensure that the entire system and all components to be displayed on the analyzer is available. So here's what we do to set up for distance to fault. Up here in the top left corner, you want to select the DTF mode. When you tap up here, you'll see the drop box to the right. Make your selection to either DTF SWR, which means your results are going to come back to you in VSWR, or select DTF_RL, and your units are then going to be return loss. You can see down now that I'm selected distance default, and my results are going to come back to me in return loss. Set your frequency range wider than the system requires. Right now, the unit is set from 1 megahertz up to 4,500 megahertz. If you have a little difficulty doing some quick math in your head, I'll explain how to change that. The next thing you'll want to do is select the number of data points. Right now I'm set to 201, but we can select anywhere from 51 up to 3,201 data points. Set your DTF info. Tapping on the DTF icon brings this window up, and this is where you can set all your distance default parameters, such as your units in either meters or feet. Set your stop distance, and I mentioned add a total length of the system, including the antenna, and add 10 to 20% on top of that. Enter the velocity of propagation and cable loss manually, or select the cable type from the cable list to populate the VP and cable loss fields automatically. When you select the cable list, there are approximately 94 pre-programmed cables in that list. If your list isn't in there, you can always add to it. Finally, the last thing to do is calibrate the unit. And here's a calibration tip. I covered it last week, and it hasn't changed from this week. So when you do a calibration, use a test cable in your measurements. Adding that test cable allows you to extend the test port to reach those hard-to-get places. And when you have a test cable, it will change the length of your measurement in distance default. And when using a test cable, calibrate to the end of the cable. And when you calibrate to the end of the cable, this is the starting point for your measurement. I want to discuss a few typical values that we're going to see in a distance default measurement. These are very important, and it will become clearer when we discuss the actual sweeps, what these values are for. An antenna at resonance typically will measure 1.5 to 1 on the VSWR scale, or negative 14 dB return loss scale. A connector, typically they come in at 1.12 to 1 VSWR, or negative 25 dB on the return loss scale. A jumper, 1.04 to 1 VSWR, or negative 35 dB on the return loss scale. A lightning arrestor, 1.12 to 1, or negative 25 dB on the return loss scale. And finally, the feed line itself, or your transmission line, or coax. A good coax will generally measure 1.06 to 1 on the VSWR scale, minus 30 dB on the return loss scale. And as I noted above, these are typical values for a specific connector by a specific manufacturer, or any of these components. You'll want to check the manufacturer's specification, because they will make a difference. So when you're going to interpret your sweeps, we want to have a test system diagram if possible. And here's my sample. I have my SiteHawk, I have my test cable. It's 1.5 meters, but because I calibrate where the red arrow is, that's actually going to be the starting point of my system. And as you can see in the diagram, I have a couple of 33-foot lengths of LDF 5-50A feed line. They're joined together by connector, and then out at the end, I have an antenna. It's a mag mount antenna and it has about 20 feet of pigtail on it. My total system length is 86 feet. So try and remember that if you can, but I will prompt you and help you remember as we go through some sweeps. So here I have a sweep. I've set up my unit. I have set my starting frequency to 700 megahertz. My stop is at 900 megahertz. I've set it to 801 data points. My stop distance is set at 100 feet. Remember from the previous slide in my diagram, my total distance was 86 feet. Well, when I add 10 or 20%, I rounded it off to 100 feet. Down in the lower right corner, you see the COR on displayed. That means that I have gone through the calibration process. So now I'm going to examine what my sweep is. If you look there, marker 1 is roughly at 0 feet, and it's at negative 45 dB. That's the initial connection point on my sweep, and you can think about the diagram as the connectors and everything appear at the top. So now looking at the yellow sweep at the red arrow, this is my feed line. And it's down at about negative 57 dB. Remember some of those values I had in my chart? What did the connector come out at? We said that a connector is typically at negative 25 dB. Well, at marker 1, my first connector is down about negative 45, so it's nice and low. Really good. I also said my typical feed line should measure at about neg 30 dB. Well, we can look across the screen and I'm down around neg 57 dB. So we are nice and low there. If I go out to marker 2, remember I had a barrel connector connecting my 33-foot sections of LDF 550A. And you see how that jumps up out there. I can see it. It's out there at about 34.5 feet, negative 40 dB. And I'm not too concerned about it. It looks like it's jumping out of the picture, but I'm not concerned because at negative 40 dB is well below the negative 20 dB, 25 dB of a connector return loss value. You might ask yourself, if I have 33-foot sections of cable, why is my marker at 34.5 feet? Well, it's a non-precision barrel, which changes some of the insertion loss. When the insertion losses are not necessarily correct, that affects your distance. So because of that non-precision barrel and a couple of other connectors in the system, that actually adjusts our system a little bit. And that's also another explanation why you want to add an extra 10 or 20% onto your total length. So let's continue on. Now we're into that second section of feed line. And all looks good. And where normally my sample test diagram showed an antenna with some a 20-foot cable attached, up here in marker 3, I'm at 67 feet, which indicates I'm out at the end of my second section of cable. But it's open. Notice I'm out at 67 feet and I have my return loss value for marker 3 is at just about 0 dB. Anytime you approach 0 dB on a return loss scale, that's indicating a short or an open in a system. And that's exactly what I'm showing here. Now, if I go to my next sweep, I start off, I have my initial connection. Here's my first section of feed line. I have my non-precision barrel. My second section of feed line. And here's my connector to the antenna. Remember, I said my antenna had about a 20-foot section of pigtail on it. A couple of things I want to look at marker 3. My distance didn't change by connecting the antenna. I'm still at just over 67 feet. The one thing to call into question here, marker 3 has an amplitude of -19 dB. And if you remember from my Viswar return loss chart for different items, for a connector, I want to be at -25. Well, being at -19, that indicates to me real quick a problem. And we'll come back to that. Whoop. And out there at marker 4, that's my antenna. And if you subtract the difference in length between marker 3 and 4, marker 4 is out there at 86 feet. Marker 3 is at 67 feet. That's just about 20 feet of difference. So you can see the antenna out there with the additional 20 feet. And our total length there is roughly 86 feet. Now here, I've got one more thing to show you. And this is why the diagram is really helpful. We start off at the first connector. We go through, we have our feed line. We have our non-precision barrel. The second section of feed line, we have the connection to the antenna. Notice marker 3, 67 feet, the connector to the antenna. Remember the previous slide, we were at about -19 dB? Well, I went out and I took a look to see what the problem was. Here, my connector was not real tight. It was loose. I fixed it. All I did was tighten up the connector. We're down well below the -25 dB I wanted to be at, and I'm actually at -35.77 dB. I go out there, look at marker 4. Marker 4 is at 86 feet. I have a return loss value of -15.55. So all is good. But what's the one thing that didn't show up in our diagram? Well, we've got this hump out here at marker 1, 16.9, or just roughly call it 17 feet. What is that? It's at -31.39 dB. It's not hideous, but it ends up, you go out in the field, you take a look at it, and we find out it is some sort of a fault. Doesn't show up on our diagram because it's not supposed to be there. And just so you know, went out, took a look, and what did we have? The fault on the previous slide ended up being a very large dent in the cable. This is one of the reasons that it is very helpful to have a diagram when you're performing a distance to fault sweep. Now, if you don't have a diagram, it's not the end of the world. You can still, using your brain a little bit and a couple of tricks, you can go out and locate the end of the transmission line. Doesn't even have to be the end. It could be some segment in the middle. All you have to do, here's a little setup. You can see the feed line, the analyzer connection. If you go out and disconnect the antenna or disconnect any segment of that cable, install the short on the end of your line or an open. That's going to give you full reflection. And you can see the spike out there goes all the way up to 0 dB. And if you remember, I mentioned anything approaching 0 dB return loss indicates a short or open in your system. And there it is, marker 2 at 34 feet, just about 0.2 dB is where my short is. And taking a look at the values for marker 2, 34 feet, 0.249 dB. Now, if you want to make sure that you really are at the point you're at, now you can go out there and take that short, replace it with a precision load. And this is going to do two things. It's going to ensure you have opened up or disconnected whatever the connector is on your cable, whether it's from the antenna or a segment of the cable. And it will ensure you found your spot Marker 2 is down about negative 41 dB, but also look how nice and flat the transmission line is all along. We're down roughly between negative 55, negative 62 dB return loss. So when you use the precision load, you're actually testing the cable as well. And that's pretty much it. How you set up for a distance default sweep and how you analyze your sweep. But we have a couple of tips I want to pass along. And maybe those of you that have used your SiteHawk in the past have run into this. Why can't I set a stop distance more than 17.5 feet? And you can see down in the lower right corner, it does give you the distance default max. Well, the max distance the SiteHawk can see into a cable is based on 3 factors: the frequency span, the number of data points, and your velocity of propagation. So down here we're set up for 1 megahertz up to 4,500 megahertz. But if you tap there on the start, that will change the start and stop frequency to center frequency and span. So you can see with a frequency span of 4,499 megahertz, if I have 201 data points selected, and my velocity of propagation is set up for 0.8, I'm going to see a max distance of 17.49 feet. If you want to see a cable 20 feet long, you're in trouble. So because the velocity of propagation is a cable spec, you shouldn't or can't really change that. So the choices you have are either to increase the data points or narrow the frequency span. If I increase the data points from 201 to 401, that'll increase my distance default max to 34.98 feet. If I increase my data points from 401 to 801, now I can see a cable almost 70 foot long. So that's what happens when you increase the data points. Now, what if I narrow my frequency span down to 1,000? Now, I can see a cable 314 feet long. If I need to see a longer cable, I narrow my frequency span again to about 400 megahertz. And that increases my distance to 786 feet. So those are just some of the tips for increasing the length of a cable you can see. Here's a good one. Don't tell me you've never had this happen. I entered my stop distance of 100 feet. Why does it display 328? Well, you need to double check your distance default units prior to setting up the stop distance, because if by chance your unit was set to meters and you entered 100, you're actually entering 100 meters. And then if you go ahead and realize you were set to meters and change your distance default units to feet, it's going to recalculate from 100 meters to 328 feet. Happens to me all the time. So just remember, set your distance default distance measurement distance units first. And another helpful hint is, when resetting to factory default, you get the option of selecting your distance units, meters or feet. So this is a good time to go ahead and do that. You won't have to worry about that when you set up for distance default. Watch your cable information. Remember how I said that the velocity of propagation, if you enter it wrong, it affects the distance? Well, here I have a sweep. My velocity of propagation is entered correctly, and it shows that I have my load at the end of my cable. My distance is at 59 feet. Well, if I go in there and adjust that velocity, and it's incorrect. Distance from all the way down to 43.9 feet. So be careful, especially if you're hanging up on a tower and you're looking at something 80, 90 feet up and can't find anything, and it turns out because you entered the wrong velocity, you might be looking at 75 feet or 120 feet. So very important to get your velocity set correctly. The other thing is when you enter the cable loss manually or incorrectly. Here I have a correct cable loss value. My amplitude is at negative 32 dB. But incorrectly shows my amplitude at negative 25 dB. Again, very important to enter the cable loss correctly. It could be the difference of a component passing or failing. And the last thing I want to mention is saving files. Files can be saved on the SiteHawk in several formats for future use. We can save setup files or a .cst. These can be saved and loaded to save time in programming the unit. S1P files are the files that we use and import into the SiteHawk PC tool. PNG and J screenshots of your sweeps, and I know most of you use this function. Save your sweeps as a PNG or JPEG, copy them off of the SiteHawk, print them out, put them in a book. 3 months, 6 months from now, you can see what's changed. Another thing about saving a CS, it can be loaded to overlay a live trace. So last month you went out, you swept an antenna, it all looked good. Now you're having some troubles. Hey, if you've saved that CST file and call it up today, taking a look here, back in the faint yellow in the background, that's when that antenna was good. Maybe there was a storm or wind damage, and now we recall that CST file, and it shows you the trace you saved in the past, and now the live trace has appeared, and you can see how that has shifted. When you save these particular files, it requires a separate operation for each. And for those of you that want a JPEG, want a CST, want an S1P, it can be a little bit cumbersome. But you can also select Save Multiple Files, allows one operation for several type of files. You do have to be current in the firmware, and we had released this with version 1.61, and this is where you would get this feature. So down there at the bottom, you touch Save Multiple Files. Check the different boxes for whatever file type you want saved. Once you've selected the correct boxes, enter your file name at the top, tap Save, bada bing, you've selected file types are saved with the same name and the correct file extension. One save operation. So to recap, we discussed what is distance default. We discussed setting up for distance default. What do I need to know? And how to interpret a sweep. And we also discussed some of the tips and best practices.